Okay, good afternoon. Sound check, just double checking. People can hear me?
Yeah.
Yeah.
Thank you. Okay, good. So good afternoon, good evening, good morning, good night, wherever you are. So I'm going to talk today more about Raft. And we want to sort of cover the following different topics, which are going to be relevant to labs. So first of all, I want to talk a little bit more about log divergence. We sort of had a cliffhanger at the end of the last lecture where we got in a discussion of figure 6. I want to resume that discussion. I want to talk about log catch-up. What happens if, how do followers catch up? Then talk a little bit about persistence, like what state in Raft actually must be persistent in storage, which is going to be really relevant for 2C and 2D. And also talk about, related to that, to snapshots.
Oh, it's off.
Yeah. If there's any questions, please feel free to ask. And then finally, I want to talk about linearizability and correctness criterion that comes up quite often and is in the paper used also in a bunch of places. And this will allow us to talk a little bit again about like how does a service use Raft. So those are the topics I'm planning to talk about. If any questions right now, please feel free to ask. And of course, always jump in at any point. Okay, so we saw last week, we started talking about Raft. We saw that the leader has sort of this job of replicating its log onto followers. And but due to crashes and leader election, the state of the system, the logs can actually can diverge quite a bit. And figure 6 is an illustration, why how that could happen. The leaders can go down, they may append some more entries, and so there's a whole bunch of different scenarios that where a system can end up in, and so the figure 6 or the figure 7 actually shows a bunch of those. And the main reason for that figure is that it actually sharpens up the leader election rule. So once a leader goes down and we need to elect a new leader, there's actually some restrictions that must be applied to actually make sure that we can actually converge on the right log in the end. And so first of all, one part of that is that any leader needs to achieve a majority. Right? And this is a part of the idea to actually avoid this brain split syndrome or split brain syndrome, so that we can actually make sure that in any 2 subsequent elections, there's going to be at least one node that participated in both majorities, because they can only the 2 majorities must overlap, and that node must actually have the operations from the recent term. The majority is important, but turns out it's actually a little bit more subtle. You might think that like the longest log, that should be sufficient because the longest log must have most information. So we just pick that as the next leader, and then we're in good shape. And that turns out to be not the case. And the leader rule is a little bit more subtle. It actually is majority plus at least as of date, but up to date. So, if the leading election is running, a follower is like the candidate is starting to run a leader election, approaches a bunch of followers, and then the followers respond with a positive vote if the candidate actually is at least as up to date as they are. And what that means is that the last log entry must actually have the same term. Or if they actually have the same term, the longest one sort of wins. And so that's the leader election rule. And we looked at this problem last week as part of the homework, like what happens if this node that was about to be the leader actually is dead, has gone, and who could become leaders. And we quickly discovered that there's a bunch of them that cannot become leader, but then there's potentially a number of scenarios in which some can become leaders. And so in particular, we identified that A can become leader, C can become leader, and D can become leader. And so then, this is probably the most important part of this whole discussion, right? Like, who can become leader?
Yeah, there's questions.
Is there? Let me hold on. Okay, good. So who become? That's the most important part. So there's a bunch of different scenarios in which A can become a leader. There's a scenario where C become a leader, and a scenario where D become a leader. Then the discussion focuses a little bit. They're like, well, at least there's one particular scenario in which one of these becomes leader. There's multiple scenarios in which they can become leader. In particular, this discussion focused on A, because like one way that A can become a leader is when C and D are down, right? Because if C and D are down, A will talk to B, E, and F, form a majority with 4. It has the most up-to-date log. You notice that even though F is a longer log, it actually is not the most up-to-date one. And so A actually will succeed in becoming the leader. And then things proceed from there. But there was an interesting question that came up: are there other scenarios in which A can become a leader? In particular, is there a scenario where, like, even if C and D are up, or reachable, or participate, is it possible that A becomes a leader? And so we can C and D are up. And so the question is, does C and D always vote for A if A is the candidate? And it turns out this answer is slightly complicated. It is not completely straightforward. So if A starts this election, presumably it will start the election in term 7. And so if the context is C and D, C will be perfectly fine with that because the A is at least up to date, and so we'll be able to achieve a majority. But it is possible, correct, that D, there's one additional rule that if D actually has, if a follower, or if a follower has a higher term, has seen a higher term, its current term is higher than of the candidate, then actually it can stop the election, because it will respond saying, like, hey, my term is higher than your height, or my current term is higher than your term, and so therefore you have to become a follower. So A will then be changed back from candidate to follower. And this can happen, correct, in the case of D, because D might actually have seen term A, and we can't really tell from this picture what actually the outcome is going to be. But let's assume that, for example, it has run once, and X has increased its term to 8, maybe didn't become succeeded leader, and then its current term will be 8, and so it will vote. When A actually asks it to for its vote, D will say, no, I won't vote for you, and furthermore, my current term is A. So A will receive that message. It's higher than 7, and so A will actually step down and become just a follower. And then at some point later, presumably, D will run, its election timer will go off, and actually it will run. And so the short story of this, the morale of this, really this picture is that it's absolutely possible that A, C, and D can become leader in different types of scenarios, and that's probably the main thing to get out of this.
Professor.
Yeah.
So I just want to ask, because I think I'm not sure if I understood correctly, but I think you said A might be elected in term 7. Is it not true that A cannot, for any reason, be elected in term 7? Even if D was down, right? Because people like D already got a majority, right, in 7.
D got a majority in 7 because it actually was able to get something done. So presumably, you're right. Good observation. So it has to be the case that there's a number of people that actually already in term 7, correct?
Exactly.
And the picture is just incomplete. We don't really know what the current term is that people have seen so far,
Yeah.
right?
But well, yeah, I mean, the only thing is like, I think like a majority of the servers already voted for someone in term 7, so they
Yeah,
wouldn't.
so presumably A will go to term 8,
Mhm.
and we'll run the election for term 8. But for the same reason, D might already be in 9, right? And so it all depends on what the current term is, what these participants are in. But the main conclusion, correct? The main top level conclusion is that A can become leader, certainly when C and D are offline. C can become a leader, and D can become a leader.
Thanks.
Good. Okay. Then so we now know that the raft can sort of enter in states where the logs are diverged, and so that needs to be repaired. And so like one key component of the raft protocol is to do that log catch up, as they call it. So I want to talk a little bit about that. And this is basically what you sort of have to deal with in part B of the lab. And so maybe easy to illustrate with this picture. And so let's it's going to make it a little bit simple. Let's have 3 servers. And here's S1. It has term 3 in index 10. It is index 11. It has no entries in 10 and 11, 12, 13. Here we have S2. And S2 has entries, 3, 3, and 5. And so this is index 10, 11, 12, and 13. 13, just to make it complete. And here is S4, or sorry, S3. And let's assume we're in the scenario 3, 3, 4, and 10, 11, 12, and 13. And I'm not showing like the indexes before 10, because they're not going to be very relevant. And let's use the timeline, these different services. And just let's start out like assuming that S2 becomes the leader, because it has the highest, it is most up to date. It has the highest term number in the last log entry. So it becomes leader. And now we need to sort of we understand how about the protocol is to synchronize these particular logs. And the way this almost happens is sort of as a side effect of either the append entries, because new log entries are appended, or because of heartbeats, which basically are append entries with 0 new entries. So let's assume that the leader actually sends a heartbeat out. In fact, it does it, correct? After every election, immediately sends out a heartbeat. And so it will send out a heartbeat. And the heartbeat, basically has no log entries, but it also indicates 2 other pieces of information, namely the previous term. So the previous term, which in this case is going to be 5, right? So, and the previous index is going to be 12. So it sends it off to the leader. S2 sends it to S3, and S3 looks at this and says like, well, let me look. My previous term is actually is not 5. It's actually 4, and so it actually sends back a message saying no. I'm alive in principle, but I cannot do your append. So I'm not up to date. And so now S2 has some information to actually bring it up to date. And the way it works is there's sort of 2 variables that are of importance. One, for every node, S2 keeps a variable next index. And next index, when it initializes, when it becomes leader, it is sort of an optimistic variable. It just assumes that the logs are actually up to date. And so when S2 becomes the leader, it actually just sets it to 13, the same value that actually it has for itself. And that's perfectly fine. because it's just a guess about what actually where S3 might be, and S3 might be behind, and then because there's no message, the leader actually learns that. And so in fact, when it gets this no message in the unoptimized version, so I'm going to first talk about the unoptimized version. The leader just decrements the next index by 1, and so it decrements 13 to 12. And then, at some point we'll send another, append entries. And this time around, it will actually say, okay, well, next index is 12, I got to send, log entry 5. And, the previous term is going to be 3. And the previous index is going to be 11. And so when S3 actually receives this message, it checks the previous term, it's 3, the previous index is 11, that all works out. It sees that it has to append 5, and so it will erase, the 4 and stick a 5 in there, and basically respond saying, yep, good. And so at this point, the leader knows that actually the log is up to date because it got an OK message back. So then there's the second variable that plays an important role in all this, which is match index, which Raft also maintains for, the leader also maintains for every follower. And so there's a next index, for S3, there's a next index for S1, and similar, there's a match index, for, S1, S2, S3 too. And this one is sort of, if you can think about this, is pessimistic or a lower bound. So when the leader actually, becomes a leader, it actually sets the value just to 0. And to indicate that basically, as far as it knows, the S3 doesn't really have any log entries at all. And so it hasn't delivered any log entries to the application. And so for S2 also has to be very careful about what actually it can be delivered to the application, because he needs to know that at least a majority of the followers actually has a copy of a particular log entry before it can deliver it. And so it just starts out to be pessimistic, but then once it learns, that, for example, once it learns actually that the follower is okay, and we've got an okay on the append message, it can actually update, the pessimistic lower bound or the match index, from 0 to actually 13, because it has learned that the follower is actually up to date till 13, and that is the next index that it expects is 13. And at this point in time, basically it has learned from 2 different. It knows that that particular log entry 5 is actually now replicated at least in 2 nodes. And so you might think, well, good, it has been replicated in 2 nodes. We can deliver it to the application because the majority clearly has it, and we're in good shape. And unfortunately, that actually turns out not to be the case. It's close to true, but not completely true. And this actually has to do with figure 8. And so I want to talk a little bit about figure 8. And the real reason what's going on here, what to make this slightly complicated, and you also should think, it's a little bit fishy. So this leader, S2, just erased a value out of the log of S3. And, somebody put that in. And so, erasing it, it seems a little bit, dangerous. And as was, and so there, and it turns out there is a corner case where you have to be a little bit careful by when you declare a message actually committed. And it turns out that basically, so and figure 8 illustrates that. So let me talk a little bit about this, erasing log entries. And what we'll see is that the rule for actually when the message can be delivered, to the application is slightly more subtle than just counting the replicas. And so let's see, actually get figure 8 loaded in. Okay, so here's figure 8, and so as usual structure. Okay, let me get back to the question in the chat in a second. So here's figure 8, and so let's walk through what the scenario here is. Correct. In figure A, log entry 1 has been committed by everybody. The S1 or S2 became leader in entry in term 2. They committed or they started appending an entry 2. Hasn't been committed yet because it's not on the majority for sure. Then in B, what actually happened, S5 must have been disconnected, hasn't heard of this term 2, became a leader in term 3, appended an entry to its log. That certainly is not committed because there's no majority. And then we end up in C, maybe the S5 actually got disconnected again. S1 becomes a leader in term 4, and then starts replicating, entry this log entry 2 to other nodes. And in fact, delivers it, it gets back, like we saw in the previous slide. It knows it's actually on S2, and it knows it actually is on S3. And it turns out, that actually you might think, okay, well, S1 knows, that actually the free nodes that actually have a copy of this particular entry, and so I might be able to deliver it. And it turns out that is not true. And there's a more subtle reasoning that needs to happen to actually commit, and namely, you can only commit. Oops, sorry. You can commit after the leader has committed one entry in its own term. And if we think about this, number 2, it actually is in term, the leader's in term 4, and so the commit rule wouldn't allow actually committing 2 immediately to the service because that actually is one from a previous term and not from the current term. And so, for example, your code to decide whether actually something can be delivered on the applied channel needs to take this into account. And the reason you need to take into account is illustrated by D and E. Where basically what can happen is that, for S1 actually you might we might actually end up in a different situation where D actually becomes the after D actually becomes the leader after, for example, S1, for example, is particularly disconnected, and it might actually start connecting. It can form a majority, and actually it starts copying its particular its entries to actually or it erases the 2s and actually copies its 3 in like the entry for its term 3 into where it used to be 2. And this is this erasing that we talked about on the previous slide. And so we'll see actually that even though T was on the majority of the nodes, right, was on the majority of the nodes, that got erased. And so the rule, and therefore the rule is as stated here, because once, this is illustrated by E, once actually S3, S1 commits an entry in its own term, and so it knows that every node, there's a majority in its own term. So at this point, it can actually deliver 4, to the application. And as a result of that, any nodes that were committed in previous terms can also be delivered, to the application. And so we see here that this raising of log entries, basically makes the commit rule quite slightly more complicated. And that's just the design decisions that the designers of Raft made. They could have done it differently. They could have counted and made basically 2 survive if they wanted to, but they decided to go for this particular approach, on the grounds that they think it's simpler. Okay, so this is a subtlety that will show up, in the test cases for the labs, and so you have to be a little bit careful with your commit rule, and that you implement it correctly. Okay, so so far, if we go back to this particular picture, the unoptimized version of this protocol is a little bit of a bummer, right? Like, if you think a little bit about this, let's look at actually what happens with S1. So let's say, let me switch things. So let's say S2 tries to bring S1 up to date. We'll do the same thing. Send in append entries, with nil entries, past term, previous term to be 5, and previous index to be 12. It will say no, right? Because it actually is at index, previous index is actually at 10 with term 3. So it will, this guy will decrease its next index, going from 13 to 12. Then we'll do the same thing again. We'll send, I guess it's going to send 5, the lock entry 5. It will send the previous term to be 3, and previous index to be 11. It's going to get a no back. Then the index goes from 12 to 11. And now basically it's going to work. And so what we see here, that basically for every log entry, we're going to have a round trip, sort of one of these append entries. And it turns out, that can be expensive. Left with, and the real question is like, can the follower be far, far behind? And let me ask that, or pause there for a second, and so you can reflect and think about that case. Is it possible that a follower can be far, far behind for a given leader?
If a new machine joins the cluster?
Yeah, if a new machine joins the cluster is a good example. Any other cases?
A machine crashed and is only coming back online after several terms.
Yeah, exactly. Maybe it comes back after a day, right? And so it might be far, far behind. And so that would mean, like in the protocol, in the unoptimized version, that you're going to go back one by one through the log entries. And so that's a little bit expensive. And so the paper actually discusses an optimization, so to catch up quickly. And the idea basically is, instead of like backing off, so as I said earlier, the next index is basically an optimistic. It's just a guess, right? And it doesn't really have to be that accurate. And so the observation is that we don't really have to go one by one back. It's perfectly fine, for example, to go a whole term back. And in fact, it's sort of logical. Maybe that is the note. Is a couple of terms back, and so we back off a couple of terms, and then we'll scan from there. So then, to illustrate a little bit how that works, let me use the following example. And I'm just going to two servers, even though there might be, we need 3 to sort of have a majority, but let's assume there's a third one, and it just plays happily along. So here's S1, here's S2, and let's see, this guy has 5, 5, 5, 4, 5, and this is 1, 2, 3, 4, 5. The indexes, and let's say this S2 has 4. It's basically all 6s, and so basically S1 is quite behind, correct? Because the only place where they actually line up is in the first entry, in the first which has term 4. And so in the unoptimized scheme, we would back off like one by one until we finally got there. And to optimize this, the paper describes an optimization. Unfortunately, the optimization is not as described in the same amount of detail as a figure 2. And so in fact, you will for 2C, actually past 2C, you do actually have to have this optimization, a form of this optimization implemented, but you're reasonable free actually how to implement it, because the paper actually doesn't describe very precisely, how you should do it, and you will have to do a little bit of work. But the basic idea is as follows. And instead of just voting or just saying no or yes, as we on the previous slide, the rejection. So if you say no, the rejection includes a little bit of more information. And that information is going to help the leader to basically back off quicker. And so it includes something what they call the conflicting term. in the response and the conflicting index. And the conflicting term is basically the, if, let me actually make this a little more clear. Let's say we're at S1, the timeline, here's S2. So S2 sends a, is elected leader in 7, correct? Because it has the most up-to-date log. It sends a message, to S1, a heartbeat. And in the heartbeat, it will say, the previous term was 6, and the previous index was 5. And now when S1 gets this, it looks at this log and sees that actually the previous term was 5. And so instead of actually, and so it will include in response, the conflicting term, like the term where it conflicts on in that index, and that was 5 for the final entry. And then it also includes what the first index of that term is in its log. So we look at this term like at 555, and the first time like the index 5 showed up in its log is at an index 2. And so we'll include that too. And we'll send that back to the leader. So here's S was our leader. And so we're going to send back 5, 2. That's the conflicting information. And the leader uses that information to basically skip backward further. In fact, it skips back, from, so initially its guess was next index for S1 was 6. And based on this information, it actually scales it back to 2. So it turns it into 2. And then the next append entries is going to include everything from 2. So it's going to include, 555. And previous term is 4, and previous index is 1. And now S1 can, in one fall swoop, basically copy, the new log entries over, the entries 2, 3, 4, 5, and that one's back up to date. And so this basically, reduces the number of sort of heartbeats, to catch up a follower by 1 per term instead of 1 per entry. Any questions?
How do we make sure that we don't, overload the bandwidth? Because I imagine if you have if you're trying to send back all of these log entries, could that cause problems in terms of packets that are too large?
Yeah, so a great question, Greg. And because it sort of indicates sort of an alternative scheme, right? That we could go back here. Is that instead of actually making this optimistic guess, why make a guess at all? Just send everything. The leader could have sent its whole log, and it would be perfectly fine. And then basically, any of the followers can sort of fish out the ones they need, right? And that would be an alternative implementation. And presumably we don't like that implementation because the log might be large, and that would be problematic. So I think the basic guess here that's going on is that in the typical situations, the followers are hopefully reasonable close together, and so backing off a couple of entries is actually sufficient. And if not, then we might as well back up 1 term, but not all terms. And so we'll send the log entries for 1 term, and that might be a lot, right? That might be a lot, and we'll see in a second how we get around that, right? Snapshotting is going to help reducing the number of log entries that we have to send. So there was a question of, do you need to implement this sort of a version of this optimization scheme in Lab 2C? And the answer is yes. Or at least I believe I haven't been able to pass the test without implementing some optimization.
So I have a question. In my code, I did the optimization by backing off to the commit. So I made the reply include the last commit index, and then I started from there. Is that much worse?
You might run into trouble in so the tests keep track of how many bytes you sent and gives you a budget. And if you're go across that budget, by too much, then the tester will say well, you're just sending too much data.
Yes.
Because in your scheme, it might be the case that I think you will send more data than really necessary, whatever necessary means. But
There is a question in chat.
Yeah. Did I say draw the wrong thing? Yeah, 6666. Sorry. Thank you. 666. I don't want the follower overriding the leader's log entries. Sorry about that. Good catch. Any questions? Okay. Okay, so let me talk a little bit about the persistence.
We have one question in the chat first.
Okay.
They're wondering why the rejection has to send back the rejected term number as well as the index.
Well, that depends very much how you actually implement what kind of state you maintain on the leader and how the leader decides to back off. You need to send some terms back because you need to ignore. If a response gets delayed for a long period of time, you certainly should reject, information from terms that are completely not relevant anymore. So I know this is a slightly vague answer, but it's really very much dependent on exactly how you implement it. Okay, persistence. We talked about persistence a little bit in the last Raft, in the first Raft lecture, where we noted that the follower can only vote for one candidate per term, and therefore it needs to remember it's who it voted for and what actually the current term is. But there's sort of a larger issue around persistence, and that came up in one of the questions that one of you just asked, which is what happens on reboot? And there's sort of two possible strategies you could think of, right? Like one strategy is, strategy one is, basically the node joins sort of freshly. So joins, basically when a node crashes and comes back up, it just doesn't participate anymore. It has to rejoin, rejoin the Raft cluster. And that means, when it rejoins, you sort of have to replay the log, or it basically has to receive every entry in the log and then replay that. And of course, like if a node has been down for, a node crashes and is down for a day or 2 days, or even if it just goes down for a second, but the system has been up for a year, then that would mean like you have to replay a lot of log entries. And so that's a little bit annoying. And so people prefer that strategy 2, which is, you can back up and you just basically participate again. So you catch up from, you start from your persistent state. The idea being that, like, if it's just a quick reboot, you crash, you come back up on, or if there's a quick network failure, and so maybe the rest moved one term along, you basically have all the state, and it should be reasonably quick to catch up. And so then the real question is, like, what state needs to be persisted across reboots? We already talked about voted for. That needs to be persisted, because you are not allowed, to vote for another candidate in the same term. But the Raft maintains a little bit more information. It also maintains the log on disk or in persistent state and the current term. And for each one, we should ask ourselves the question, why maintain it on persistent state? Because it means that whenever we update that state, whenever we append an entry to the log, or whenever we increment the term, or whenever we change for the word, we actually have to write to disk or to stable storage. And stable storage is expensive, and so it's very likely that, for example, the writing to stable storage could become a bottleneck. So we're already talking about voting for, so I'm not going to cover that, but let's talk about the log. Why does the log have to be written to persistent storage if we reintegrate? Another way of questioning, let's say we don't write it to stable storage, what would break? Yeah, someone in the chat, Shushi answered this question, which is you could lose the majority on the committed write entries, right? So here's the scenario. The Raft replicated the operation on a majority of the nodes. So somebody, majority of the nodes actually committed to actually having accepted that log entry. So the leader sees the commitments. It delivers the message with their operation on the applied channel to the servers. The server executes the operation and lets the client know the operation has succeeded. So now, basically we exposed the fact that this actual operation was actually replicated in the majority of nodes to the client. And so if the followers that actually received that entry did not put it on disk, so that when they reboot, they still have it, we could run into the case in exactly as the answer in the chat that we lose the majority on a committed entry, and that entry will not be delivered on the remaining replicas to the service. And so the client will see something strange where it sees that an operation that it did actually happened, but a little bit later, actually it doesn't, that operation hasn't happened. And so it actually is important that this actually is on stable storage. Now, we basically promised the leader to commit it. And we cannot back out of that promise. Okay. Any questions about this? Why do we need to remember the current term or on disk? Why does that need to be stored stably?
Well, the term, you vote for a different person in every term. So if you don't keep track of what term it is, then you don't actually know who you voted for, right?
Yeah, exactly. You don't really know who you voted for. That's one problem. Also, current terms always have to go up, right? You cannot go down in term because you're going to use that to detect RPCs from stale leaders and stale candidates. But this always has to go up. Okay. Any questions about persistence?
Actually, yeah, I guess I have one, which is more about the way you laid out stuff, but you say there's two strategies, right?
Yep.
Replaying the log and starting from a persistent state.
Yep.
And so the way you describe starting from a persistent state, do you replay like I guess it doesn't say in the slide, like if you does that assume you also have like the snapshot of your state?
I have not talked about snapshots at all yet, which we'll talk about in a second. That's actually the next topic.
Okay, but
the point is, okay, there's two strategies after a node crashes. There's two ways to treat that node. One as a complete new node that never existed in the system ever. And so when it comes up, you add it to the cluster as if it's a new node. So basically the cluster goes from, let's say you started with 7 nodes, one guy crashes, the cluster has 6 nodes, it just happily proceeds, whatever the other nodes do their application and all that kind of stuff. And then the 7th node actually comes back up. And so there's two ways of, then join, one way is to say like, well, I just forget everything I did ever. I'll join the cluster again, and the other 6 nodes will bring me up to date. They will send the log to me, and I'll redo the operations. And that can be costly, even with snapshots. So the second strategy is to say, well, if the same node 7 comes back up again, it tries to reintegrate with its persistent state that it has. Basically in the hope that, if, for example, it went down for like, a couple nanoseconds, a microsecond or a millisecond, there's basically not much catching up to do at all because it already has all the state.
But it would like, aside from the log, there's also like a state machine, right? That you've been like applying changes to.
Yeah. So yeah, let's talk about that. So I think this is the next topic.
Okay.
I think you're, what about service recovery?
Sorry, I actually have another question on persistence.
Yeah.
When does the server decide to persist?
Good. Great question. What do you think? I'm sure you thought about this.
I mean, I think a simple answer would be every time one of these variables changes, but that seems like a very costly thing to do.
I think that this is the correct answer. Whenever one of these variable changes, you actually flush it to disk, or you write it to in our case, correct, in the labs, you write to the persister module.
Okay, and
so for example, when the leader, accepts an entry, through start and appends it to its log, it actually has to persist that entry.
Okay, and so does the persisting work incrementally? So it like once you get a new log entry, you append, or does that like take the entire state and like rewrite it into the file?
Okay, in real life, we append, right? And you would not rewrite the whole log. You would just append that one entry to the log, and that's actually one of the reasons that logs are cool, because you can just sort of append at the end incrementally. In our lab, the whole thing is fake. The persister actually doesn't really persist. It keeps the object around, between crashes, because crashes are also sort of fake. The tester basically, stops nodes, restarts them, and basically gives them the new state. But in the real system, you would append. So the log would be a file, and you would append an entry to the file.
Thank you.
Yes, we actually, you all have to, in a real system, if you append a log entry, you first append the log entry and then you respond. Like, so in the append entries, if you update the log, and you append if append entries on the follower that receives a new set of log entries, it appends them to its local persistent log, and then it can respond, because it would be bad to respond before appending, because then you might lose, if you responded before appending, you might run in a situation where just before actually the actual append happens, you crashes, and so you actually did not persist the log entries, and so you would, you could lose committed entries. Okay. Okay, so how about service recovery? Right, so the service keeps its own state. Like, for example, in Lab 3, you're implementing a key value store. And so the key value store maintains basically a hash map from key to value, and you need to replay that state. And again, there are two possible ways of going about it. Strategy one is to just replay the log to actually reconstruct that state. So basically, if you're, this is sort of similar to the strategy one on the previous slide, you just take the log, you just replay all the entries in the log, and that should, basically create exactly the same state as before, right? Because the whole point, right, of this replicated state machine approach is that all the operations are executed in total order. The operations have no side effect. So if you start in the same state, like nothing, and replay all the operations, you should end up exactly in the same state as any other node. And so that's one possible. And so that is one way to recreate the state. And obviously this is expensive. If the service actually has been running for a couple of years, and you have to replay the logs from the beginning of time, that is not so desirable. And so clearly people don't really follow strategy one, but they follow another strategy, and which is like basically making periodic snapshots. And there are two reasons to doing that. One, to basically reconstruct the server state in a fast manner. And the second reason to do that is to be able to compact the log. Even the Raft state itself can be cut off, or the front of it, the prefix can be cut off. And the basic observation is that if the application is running for a while and it just has applied, say, the first 1,000 operations or the first 1,000,000 operations, then the state that is constructed at that point, the state will contain all ops, say through I, where I may be 1,000 or 1,000,000, whatever, whatever that's so. And so one way to think about it is that there's sort of a duality between state replication and log replication or replay. You could save the state after 1,000 operations, and then you got exactly the same thing as actually reapplying or redoing every operation from 0 to 1,000. And so this means that like once you have a snapshot and you store the snapshot stably on disk in persistent state, you can cut off, you can cut the log through I. And so this allows you to control the size of the log, basically by periodically asking the service to actually take snapshots, and then the service telling the Raft library, yes, I've taken a snapshot through I. Then Raft can say, okay, good. I just don't have to remember anything from I or until I. That means, of course, that the snapshot has to be stored on stable storage. And this is also good for recovery, correct? And so it makes our recovery scheme slightly more complicated than I just described in the previous slide. What has to happen is that when a follower comes back up after a quick say reboot, it loads its persistent state. That includes the persistent state that we talked about on the previous slide. That's this information, but also its last snapshot, installs that last basically loads that snapshot into memory. The service does. And then, we can sort of replay any log entries to basically bring the follower up to date. Okay. Any questions about this?
I had one question. I'm not sure if I'm going to be able to phrase it super clearly. But I guess, like, I was under the impression, so I guess, like, does this not break some layer of abstraction that previously existed between the application on top of Raft and Raft itself, where it now needs to understand how the state machine, like how to apply commands to the state machine instead of just like giving commands to some external state machine? Yeah,
great observation. Clearly, there is some, they have to play together, correct? The Raft library and the service. Because first of all, if the service lies about gives the wrong information about how far it has applied, then we get inconsistent results. But anyway, so we don't assume liars anyway, but it's clearly the case that the service and the Raft library have to cooperate, and you can call that an abstraction violation. I think the reason to do it is to limit the amount of state that the Raft library has to maintain. Otherwise, the Raft library wouldn't know when it can cut the log. And so there's basically no way around it that the service actually tells it, well, I got a snapshot through I, and so it's okay for you to remove log entries from 0 through I. And you'll see that. And so this is maybe a good point. This is going to come up in 2D, right? Like lab 2D is all about snapshots and log compaction, as it's also called in the paper. There has to be some API between the servers and Raft to be able to collaborate. And basically in 2A and 2B, that API, in fact, even in 2C, that API is extremely simple. The only API that exists is basically delivering log message on the apply channel, right? And almost nothing flows down from the servers to the Raft library, other than that the service may start and Raft, tries to append an entry to the log using Raft start. And so in 2D, there has to be a little bit more of an API between the service and the Raft library. And it turns out like you can design that API in many possible ways. There are quite a number of ways of doing it. There's not particularly one. And the paper doesn't lay out what API you should use. The paper actually says nothing about this. And so it's up to you sometimes up to us, to figure out what the API is. And to be able to do 2D, we have to declare an API between the servers and Raft. And you'll see once you do 2D, that API has some funny, might be a little bit more different than you might expect it. And we had to pick one particular API, and in that API, there's an operation called conditional install that has semantics that allows you to change the Raft state and the server state atomically in one single operation. And that partly that operation exists to try to limit the abstraction boundaries. Okay. And it turns out you can do it in different ways. You don't really need to, you could have written it in different ways, but I personally think it's actually one of the more simple ways of doing it. But that will become more clear in 2D, and you'll see indeed that there's sort of an interaction between the service and Raft in a way that they have to play along. Could you repeat when Raft communicates with the service in the snapshot process? So the snapshots are driven by the service. So the service just says once in a while to Raft, I've made a snapshot, here's my snapshot. And this is a snapshot that includes all the operations through I. And then Raft, writes the snapshot and truncates its log, to I, and writes all that information to disk. And that's basically all what happens sort of in regular operation. Periodically snapshots happen, snapshot happens. Then there's the other case you will have to consider is like when a reboot happens. And so when the follower reboots, it actually reboots from its persistent state, and so including its snapshot. And so when the follower reboots, basically loads the snapshot from memory, from the persistent disk, and actually reconstructs the application state, the key value store. And you will do this in lab 3, so this is not going to be an issue in lab 2. The only thing that is going to be an issue in lab 2 is that because the followers, because the log has been cut, right? Like, instead of like having all the entries from 0 to I in the log, plus more, so I, n, the log has been cut, from I to n, right? And that's a part of the log compaction. That also means that if a follower is far behind, like for example, a new node joins the system and doesn't actually have the beginning of the log nor the snapshot, then the Raft has to communicate the snapshot to that follower. So in the case that the follower is before I, because it rejoined the lab, and it rejoined the Raft cluster, the leader actually has to send the snapshot to the follower, and the follower basically starts from there. And that will show up in 2D. And so there's an additional RPC called the snapshot RPC, or install snapshot RPC, that's described in the paper, and that you will have to implement in 2D. In fact, this brings me to a good point. Actually, let me first go to Okay, so it basically brings me to the homework question, right, which is, here's the install snapshot RPC sort of equivalent of figure 2, but then just for the snapshot RPC, and you actually have to implement that in 2D. And one issue, right, that came up in the, which was the homework question for today, is it ever possible in Raft, or what avoids it if it's not possible, that the state machine rolls back? Yeah, so for example, a leader sends maybe, maybe an old snapshot shows up, at a follower. Is it possible that, if it's possible, that the follower would install that snapshot and then implicitly basically roll back the state machine, right? Maybe it already has seen more information. Clearly that seems not right. And so really the question is, how does Raft get around it? And so maybe this is a great place to actually do a quick breakout, and you can debate, that homework question for a couple minutes, 5 minutes, and then we'll come back and we'll talk about a little bit more about snapshots. Lily, would it be? Let me.
No, Lily. How about I try? You can make
Yeah.
me the
Okay. Let
host,
me.
and then
Okay.
I'll go for it.
Yeah. Hold on. I'll probably have to make you. Host, and then you can do it. Okay, you should be host now.
Awesome. All right, should be
Okay,
good.
good. Yeah, thank you. Susan works. Thank you, David.
And I'll go ahead and make you host again.
Yeah, that'd be great. Thank you.
Perfect.
Let me see. I gotta reshare my screen. Maybe. Yep. Let me see how. Okay, everybody back online? We're good to go. If somebody can respond, that'd be great.
I mean,
I can hear
I'm
it.
here.
Okay,
but,
good. Okay, great. I hear that sometimes people, because of the breakout rooms, just get randomly dropped out of Zoom. It's a little bit unfortunate. I think the TAs have some similar experience in the past rooms breakouts, but hopefully, I don't know exactly what to do about that. I guess for a class in fault tolerance, it's a little bit unfortunate that people get just dropped. Okay, so I think the homework question this time around was reasonable, sort of straightforward. Clearly it has to be the case that you cannot install an old snapshot because a service that might have had a more recent snapshot might have responded to the client saying like, yeah, your operation succeeded. And then if you would restall an old snapshot, then you basically back out to the state and the client would see there's certainly an old version of the service. So that's certainly not legit. And so just a little bit, you should definitely reject old snapshots, but you have to be a little bit careful. If the follower has a log that goes beyond the snapshot, you have to keep that remainder part of the log because basically you have promised to a leader that you have accepted a message, and so you can't delete the rest of the log that is not covered by the snapshot. Okay. Okay, so then let me return.
We had a question actually.
Okay, go ahead.
So it says in the paper, right? If the follower receives a snapshot, that's a prefix of its log, right?
Yep.
The log entries covered by the snapshot are deleted, but the rest are kept.
Yep.
In that case, is the state machine wouldn't be overridden, right? In this case.
Okay, so the interesting question is like, how does the snapshot get communicated to the state machine? And as you will see in lab 3, that it goes over the apply channel. And so the state machine will get the snapshot over the apply channel, and then it's up to it to do the right thing.
Okay.
Okay.
Thanks.
Okay, good.
Wait, just a follow up on that. Sorry.
Yeah.
Though I was a little bit, so that makes sense to me. The part that I was confused by is in the figure 13, like the box that describes install snapshot RPC.
Yep.
On 6, it says if existing log entry has the same index as the term snapshot last include entry. Hold on, I might have just misread it.
Okay, so why don't you keep thinking about it, then we can.
Yeah, if I have a question, I'll ask.
Yeah, we'll take it offline, and we'll do it right after lecture if you want to. Okay, I want to go back actually for a couple minutes, that we have remaining, and talk about actually using Raft, which is sort of a discussion that we're already basically having here for a service. And so again, I'm going to focus on the replicated key value service. That is going to be the topic of lab 3. And so just to go back to almost like one of the first boards that I drew at the beginning of the Raft lectures, here's like our boxes that correspond to the 3 replicas. And each replica, correct, has a sort of split in 2 pieces. One is the service part. And one is the Raft library. right? And we know that basically they communicate these two through the applied channel. And that's the way the information flows from Raft to the service. And so clients, interact, with the service, not directly with Raft. And so we have a client here, that sends, operation like a put operation or a get operation to the service. The service receives, this operation, and it basically calls start, for that operation. Then Raft does its chit chat, with the other Raft libraries. Messages can flow back, and at some point the operation is committed, and then it actually is, Raft will say like, hey, this operation is ready to be committed, sends it on the applied channel, and the service then basically execute the operation and send the response back, after it executed the operation, the response back to the client saying like, well, the value for the get, key 20, is this, right? So this is a get operation or put. And this is basically the value for the get, or okay if the put succeeded. Okay. And then we also discovered in the last lecture that it might be the case, right, that the client sends an RPC to the service, and the RPC disappears, and so the client must resend, and by the time it resends, actually the leader might not be the leader anymore, and so in that case it has to sort of redirect itself to another leader. And so basically what there is a little bit of code, the way to think about this, there's a little bit of code at the client side that sort of understands replicated state machines a little bit. And it maintains some information. It maintains like who's the leader and who are the other followers. And so that can switch between them if necessary. We also, last time we talked a little bit about that it's possible that operation can be duplicated, right? Because the client may send an operation, put operation to the service, but the client doesn't get a response, but the service actually received it, so it went through, went through the whole operation sequence, starting the Raft append, going through the Raft motion, and then basically sending it out to the applied channel. And so basically, the client actually might send a second one. And and basically for the repetition, that might actually go through the Raft library too. It comes out in the applied channel, and so you have to do some duplicate detection. There are multiple ways of doing it, but either way you have to do duplicate detection. And so in addition to sort of maintaining some state about like what the leader and the followers are, the put and get also actually have an ID associated with it, and the client needs to maintain what is the last ID that it actually is trying to get through, and that is used to actually do duplicate detection. And this little piece of code is often called a clerk. The clerk that interacts, with the service, and that does a little bit of work, to collaborate with the service to actually get the right thing done. And so we have multiple clients, all have, a clerk library, if you will, which is a Go package, and the clients basically talk puts and gets, over that interface, and inside of the clerk actually maintains these IDs, or maintains one ID for the outstanding put and get operation, as well as some information about like who's part of the cluster. Okay, does that all make sense? So that's sort of the basic structure, correct, and like how Raft fits into a larger picture. The one question that comes always up is like what is the guarantees that the servers and the clerk together make to the clients about these put and get operations. And so this really means, what is the correctness criteria? And the way we always have described this so far, we've been reasonably sloppy about it, or I've been sloppy about it. And basically I've said is like, well, it should behave like a single machine. But even that is sort of a little bit of an imprecise definition, because what happens if two clients basically at the same time, execute a put or a get operation, and what actually is the correct outcome of these operations? So we really need a sort of a little bit more preciser, I think like behaving like a single machine is the right intuition, but we need a little bit of preciser definition. And this definition, you saw the term used in the paper, and this definition is called linearizability. And linearizability is basically a spec, a specification of what values a put and a get operation can return. Particularly since put doesn't really return an operation, is really what get can actually return. And it basically says like what are allowed things to be returned and what are things that are not allowed to be returned, independent of actually how you implement it. It's just like purely a specification. And it basically has three components to it, linearizability. Linearizability says like if you have to look at some sequence of operations, some of them executed concurrently, it has to be the case that there's a total order. So you can arrange all the operations in some total order. Precise operations. Two, it has to match real time. With that, I mean that if an operation completed before a second operation started, even if those operations are different machines, it has to be the case that in this total order, the first operation shows up before the second operation. And that sort of makes sense, correct? Like if it behaves like a single machine and you start an operation after another operation, then the single machine would always return the results of the first operation. So, and then finally, a read operation. So this is like in our case, in the key value server, it only has one read operation, namely get. But the read operation should always return the results of the last write. So in our case, we do a get operation, and the put operation happened well before it and completed well before it. Then that get operation should observe the last put. Okay, so this sort of these are the three conditions that whether determine whether a system actually has linearizability. And you can think about linearizability as well. Well, it just behaves like a single machine. So let me make it a little bit more concrete because this is a little bit abstract. And the way basically people think about linearizability or like argue that a system has linearizability is we're looking at particular histories or executions and then see if you can use histories, if you can turn that into a total order, even though the operations actually might have executed concurrently. And so let me give you one example, a very trivial example. So let's say we have three clients, C1, C2, C3, and they do a bunch of puts and gets. So typically the way you basically say there has to be some start point where the operation started, and there's some end point where the operation ends. So for example, when actually the client actually gets the return from the service. And so let's say this is a write operation, to the variable X, and we write 1 to it. So the client 1 started at some point in a write operation to the variable X to write 1, and it ends, at some point here. Maybe it did a second one, and writes 2 to it. And then maybe we have all the action with linearizability is when operation happens concurrently. So some operation starts before another one actually finishes. So for example, we might have the following operation. Client 2 does a read operation. In our case, would be a get. And there's a read of X, and the value returned by this operation is 2. And then we have a similar sort of situation where on client 3, it actually starts an operation, a read operation, and it reads X, and it returns 1. And let me make this a little bit more clean. The read operation actually returns before the write 2 operation starts or ends, and same from RH1. And then the question that always comes up: is this a linearizable execution? And if it's linearizable, then basically it means like if this could happen on a single machine too. And so could this happen on a single machine? And we can just like abstractly think about it without actually having, is this a legit outcome for basically what we need to look at is the outcomes of R2 and for C2 and RC3. Is this a legit execution?
I'm not sure. I don't really know what it means for a write to take like a long time.
Well,
Or
like think
for a
about
read to take a long time for that matter.
Yeah, if you think about from the client perspective, correct? It sent a request to the service, so that's the starting of the write, and it got a return value at some point from the service, and that's the end of the write. And so in between, all kinds of stuff happens, right? It went actually into the servers, put it into Raft ran, it went to the apply channel, blah, blah, blah. Lots of stuff happened. But we don't really care about exactly what the implementation does. At some point, it got a response. And so you can think about this, there's basically 3 concurrent clients, they issued concurrent operations, and we are wondering if this is actually a legit outcome.
I don't think this could happen on a single machine because the write for 2, it finishes after the read starts. Oh, sorry. Yeah, that's right. But it seems like the write should happen before the read. And in this situation, it couldn't happen if the write started after, if the write finished after the read started. Yeah.
Yeah. Okay. So one way to think about it is that we can move. We have to construct a total order, correct? And if we can construct a total order where all the operations line up, then it's a valid linearizable history. And so let's construct a total order, and then go back to this question that you just asked. So a total order, here's a total order that I'm gonna do first the write operation, then the read x1, then the write x2, and then rx, the read of x2, right? There's a total order. All the operations are now happening, sequentially. And, we just need to check whether this total order is correct, corresponding to the linearizability definitions. Well, it has to be the case that operations that start, if an operation starts after some other operation ends, it needs to be after in the total order. And so we look at this. Let's look at this. This one must start after wx1, and that is true, correct, in this total order. Rx1 must start after wx1 because it actually returns the value, correct? And in our total order, that is also the case. Rx2 must start at wx2 because it observed the result of this write, and that's perfectly fine too, right? We can basically, one way to think about it is that even though they execute in this way, we can sort of rearrange things to sort of fit the total order. And so if we think about this, then this is a total legit execution where the operations form a total order. And so this is like what a single machine would do. So a single machine could execute the write double x1, read x1, write x2, read x2, and we all perfectly fine. Okay, so let me make it helpful to think about a history that is not linearizable. So let me look at a second one. And I'm going to come back on this on the first day anyway, so don't worry if this not makes sense yet. But here's another one. I got C1, same thing, write X1. I got a C, and here write X2, and there's going to be a read that actually goes in read X1, and I'm sorry, read X2, and then I got a C2, C3, and the C3 starts after the other read and returns 1. And the claim here is that it's not possible to construct a total order that matches a linearizability. And in one way, one indication of this is that this read, right, that returned x1 started after the read that returned 2. And I will make this a little bit more precise later, but in a real, single machine system, that could have never happened, right? Because that would have meant that the value changed between Rx2 and Rx1. And with these few operations that we here have on the board, it has to be the case that this Rx1 happened after that write. And this write must have happened after that write. because they're in total, we have to respect, the ordering of the single of C1. And so there's no way to basically slot, RH1 in the total order. According to this picture, it should go after RH1. But that can really not be true, because if it got RH after RH1, that meant it's also after WX2, so that must have read 2 and not 1. And so this is not a linearizable history in execution. Another way of saying that is that basically what is RxN returning here is really returning a stale value, correct? And that is not allowed if a machine behaves as like a single machine, or a replicated service behaves like a single machine. And so I'm going to come back, this to on the lecture when next week when we talk about Zookeeper, because this is going to be a very important, like this notion of linearizability is sort of a thing that shows up prominently in the paper, and this notion of stale values also shows up prominently. And since I'm running out of time, I'll resume that next week. Okay. Any further questions? And people that need to leave, please, feel free to leave. And in fact, I hope you did. You don't want to be responsible for that you miss other classes.
Is this considered like, what type of consistency is this considered to be? Like strong consistency, event consistency?
This is considered to be basically strong consistency. And what it really is sort of a precise definition of what strong consistency is. So like our intuition about what strong consistency is, namely behaving like a single machine, the precise definition that people use in the technical literature is linearizability.
How did they decide to have that property? Like, why did they decide to have that property?
There's a couple of things. One reason, the reason, okay, so it makes sort of sense, so if you think from this point of view, like you want to make a replicated system behave like a single machine, or an unreplicated machine, and you want to only allow outcomes that actually correspond to executions that the single machine could have done, then actually linearizability is a very intuitive definition for that. The database world has also some other terminology like serializability. This is also a term that will show up in the term later. And basically the only difference between sort of linearizability and serializability is that serializability doesn't require that it matches real time. And so people have sort of different definitions of strong consistency, if you will. And the one that we'll see most prominently is linearizability, which corresponds closest to like the machine behaves, the replicated service behaves like a single machine.
Thank you.
You're welcome.
I have a question about what happens during like a network partition.
Yeah.
So I know, like, so if a leader gets partitioned completely on their own, they'll eventually time out. But if they have sort of like a few followers with them, they'll stay the leader, and they won't be able to commit anything because they'll be in a minority.
Yeah.
And there'll be a new leader, and there'll be so. Will that leader ever sort of recognize that maybe it's a stale leader, or do we just assume that eventually, if the partition goes away, it'll figure out? Because like I'm worried if there's a client that's talking to the stale leader, what does that client do?
No, okay, so this is a great question with this picture here. Hopefully it will help. So the client will talks to this guy, correct? Like who's the leader? You see the picture? I just want to double check that you can see it.
Yeah, I can see it.
Okay, good. So let's say this first box is the leader. Client talks to that leader. The leader can't commit any operations, correct? And so it won't communicate anything on the applied channel, and so it will never respond to the client, right? Because there's like no operations actually its operations are not being executed. And so the client will just retry and just keep retrying forever until the client actually maybe tries another one of the other followers, correct? It maintains who else is actually in the group, or until the network heals. And the leader actually could commit an operation.
Gotcha. Wait, so doesn't the leader immediately reply though saying, I got your request? Or does it waits
No,
until
no,
it's
no, no.
committed
In
before?
in lab 3, it doesn't communicate with the client until it actually has processed the request. And which means that the operation actually has run through Raft and come out of the applied channel and has to be executed by the service.
Okay.
Does that make sense?
Yeah, so then the client could just implement a timeout where they're like, if it's a certain amount of time and they haven't received the commit, assume that maybe I should try a different node. And then if it gets the new leader or a follower of the new leader, it'll be back to normal
Yeah, so for
operation.
example, so this clerk, that's exactly what this clerk sort of does. Sort of plays along with the service to actually do what you just said.
Got it. Okay, thank you.
You're welcome.
Sorry, can you repeat again what the clerk does?
The clerk is a little bit of like a stub or like a little library that the client links with. And so the client calls puts and gets. And the clerk actually is the interface that it talks to. And the clerk can keep some information, like who's part of the Raft cluster. And so who's the leader and who are the followers, at least what it thinks is the leader and the followers. And when it sends an RPC, to the service, it sends it to the leader, but it thinks is the current leader. And the service, whatever it thinks is the current leader, the leader might actually respond saying like, hey, I'm not the leader, you should send it somewhere else. And then it will try one of the others and updates its information. It also will tag every put and get operation that it receives from the client and that sends to the service with a unique ID. So that the service can do duplicate detection. And this all comes up in lab 3. So you'll see there. In lab 2, there's no real clerk because the tester basically sort of sits on top of directly on the Raft interface and doesn't really interact through a clerk. But in lab 3, we'll interact through a clerk.
So how did the clients generate unique IDs that don't conflict with each other?
Big random numbers.
Okay, so we're just guessing and hoping rather than actually guaranteeing some sort of like incremental.
One way to make it more guaranteed is, for example, take your IP address and append a random number.
A question about the homework question.
Yeah.
So I thought that it could go backwards in time. Like I read the paper and it said on page 12, let me pull it up. It said that if there's a conflict, right, then the follower just discards its entire log and it's all superseded by the snapshot. So I wonder why.
Let me guess. I don't really know exactly the sentence what you're referring to. I have to look it up again.
Oh, it's on page 12. It's at it's towards the end of page 12, the second column here. So the second to last paragraph.
So the log can go back, right? But not the state machine.
The log can go back, but not the state machine. Oh, is the state machine like the committed entries, right?
Yes, the log can go back because of uncommitted entries. Uncommitted entries can go back. This is like this whole erasure stuff that we talked about earlier.
Okay, so actually the log can go back.
Yeah.
But not the state machine, which is basically what you committed already.
Yeah, and the log will never go back. We'll never bail out of committed operations, correct? It can only bail out of erase uncommitted operations.
Yes, that is right. Okay, got it.
So that's what I refers to.
Can I ask a question about the third slide?
Yeah.
I guess the one right before this one. Could you just walk me through real quick what match index is doing on the right, like when S2 is communicating with S3?
Okay, let me.
So it starts out as 0.
Yep. So hold on. S2 is communicating with whom?
S3.
Yeah. So basically, okay. So here, match index is 0, right? Like so, and let me write it down as 0.
Yeah.
Okay, and then it gets an O back, so match index stays 0, right?
Okay.
Nothing there, but now it gets an OK back. So what does that imply? That implies that, what did it send? It sent a heartbeat, correct, with for index 13, and include and the S3 responded okay. And so it means that basically S3 is up to date through until 13, correct? That is next index that it actually has that expects 13. And so the S2 knows now that its log matches until 13 after this message.
Is it until 13 or until 12?
It matches till 13. So the next thing that will be sent will be go in index 13.
So
that
next
means
index
12
and match index are going to be 13.
Yeah, the next index is not used yet, correct? Means empty.
Okay.
So basically, they wait. You can do it either way, correct? You can either say the last one or the first. That's going to be or the first next one. And in this case, they go by the first next one.
So in this case, both of them are 13 for the next one.
Yeah.
Okay.
So basically, if you can think about this at this stage, correct, before like all the green stuff has happened, the match index for 3 is 13, and the match index for itself for 2 is also 13.
Got it. Awesome. Thank you.
You're welcome.
Actually, can I ask a follow-up on that?
Yeah.
So when it sees that something matches, so for example, here on position 11, it saw that it matches, then it is a guarantee that everything before that matches too?
Yes, correct, because hold on, let me double check. You're talking about this message?
Yeah, about like when it says okay, it checks index 11.
Yeah,
Yeah.
correct, because that is the whole reason that this previous term and previous index are communicated, correct, to the follower to make double check that it can only respond to okay if indeed is the case that in the previous index 11 actually turned free. And if that's true, that means that basically everything before that must match. And this is like this, whatever their whatever the statement they call this invariant that they basically maintain that like if something matches at like one index, then everything before that must match too.
Oh, okay. This is the invariant. Okay, I see. Oh, and I had another follow-up question. It was related to the question that on the lecture question that I wrote. I asked about the copy on write for creating snapshots.
Yeah.
And I think I don't really understand what is being copied. Is it the page tables or is it something?
I think I responded to an email, but I'm not sure if you've seen it.
Yeah, I read the email, but I just didn't understand.
Okay,
Yeah.
good. Okay, good. Hold on a sec. Let me catch my breath. The scenario is snapshots can be expensive because the snapshot might be large. Okay, if it's a gigabyte, key values, page table. Oh, sorry, not the page table. If it's a gigabyte, key value store, then you need to write that gigabyte to disk, right? And while you're writing it to disk, if you don't do anything clever, you cannot process any other put and get operations that come in through the channel. So let me actually pop up this picture. Correct. So basically, the service decides at some point to make a checkpoint. If it's a gigabyte, you have to write a gigabyte to disk. That's expensive. So the plan, I think the plan that the paper is hinting at is that what the service does, it calls fork. So when it wants to make a checkpoint, it calls fork, and fork creates a copy of that process, right? So now we have the operating system running, and we have now basically two processes that correspond to the this application, right? So the service Raft, and this is the copy, the child. The operating system uses copy and write. So when it made a copy of that second process, it just copied the page table, but didn't copy the physical memory. Right. So basically, these two processes share the same physical memory, which holds, our key value store, right? And so now the idea is that the child, when it starts running, it starts making a checkpoint or snapshot. I can just write out, the key values or the key value store to disk. And in parallel, the parent can just start processing new, get and put operations. Because if it does a put operation and it wants to modify it will write, to the pages that correspond to the key value store, that will result in a page fault, right? And so the OS will get a page fault, and so the OS will copy that page at that point, and then the first the parent process can just update it. And this is all transparent to the child, right? Because the child had a consistent snapshot of the whole address space at the point of the fork. And so this allows basically the parent and the child to run concurrently, still make a consistent snapshot, and the parent to actually make process new put and get operations. Is that more clear? Hopefully.
Oh yeah. Okay, I see. So we copy and write the memory that holds the key value store. Okay. I see. Yeah, this makes it very clear. Thank you so much.
You're welcome. Any more questions? Is there anybody?
Yeah, I have. I guess this is sort of a weird scenario, and I'm not sure if this could actually. But what if? So imagine that we're always in the same term, and then you get to a point where some nodes have disconnected, but they're still in the same term. The leader's still in the same term, and then at some point they will do a snapshot, and then all the logs will be compressed, and then they keep going forward, and now the logs are being populated again, and then let's just say 15 logs have been added, and then after 10 they compress them, and then they're at index 5 again, and then the other nodes join back in, and they're also at index 5 of the same term. Is that a problem? Like how does it's almost like they're on a snapshot epoch of some sort.
Okay, so well, the snapshots correspond to an index, right? So
yeah.
So okay, let's draw out, like maybe draw out your scenario. So we got a server that has some log, and maybe I think you talked about 10, and it took a snapshot at 10.
Yeah.
Yeah. So let's say that basically, yeah. So basically, the first 9 operations, or maybe including 10, are in the snapshot. And then okay, so there's another node that is same term. So all these entries have the same term, right? Like whatever, 1 1 1 1 1 1 1 1 1, right?
Yep.
And so this node actually, but this node has only through 10, correct? And this guy has through 15. Let's say. I think that's what you're saying, correct? Actually, so here were no ones, but here's a 1. So.
Well, I think my thought is, well, here's a question I could answer. When you take a snapshot, do you reset your index, or do you keep counting?
You keep counting.
Oh, okay. I was imagining it was like an array, and your index goes backwards, so that it would be possible for you to have 2 different entries in the same term with the same index.
Yeah, that's not allowed. Absolutely not.
Right. Exactly. Yeah. Okay. I see. So. Okay. That makes sense. So when you ever reset the index.
Yeah, when you cut, like this part of the log, the index stays at 10.
Got it.
And so, in fact, when you do this in 2D, this is going to be slightly annoying, because you presumably take advantage of the fact that the start of the log is at 0, and what you're now going to get is that the start of the 0 log might be 10. And so you will have to fix.
You have to have an offset of some sort.
Yeah, you will have to exactly. You have to add that offset everywhere.
Yeah. Oh, and then last thing, really quickly, I think the reason I was confused earlier was in the code for lab 2.
Yeah.
There's a comment that says we're supposed to return immediately from start.
Yeah. Well, yes. Meaning you. Okay, so let me go back to this picture here. Yeah, hopefully it's getting really crowded. So we get an operation correct, and we do the start operation. We call start.
Oh, return immediately doesn't necessarily mean reply. Is that
Yeah, exactly.
Is that the idea?
Yeah,
Gotcha.
exactly. It just means reply back, return to the service, not to the client.
I see. I see. Okay. Gotcha. I guess operating under the assumption that a return always is necessarily a reply, but that's not always the case.
No,
I
it's
see.
not the case. I think this will become more clear in lab 3 than in lab 2. Because lab 2 is a little bit weird, correct? There's no application really.
Yeah. Yeah. Okay. Well, thank you. This was really helpful.
You're welcome. Happy.
Appreciate it.
Yeah.
Have a good one.
Yeah, you too.
Bye.
Good luck with the labs.